I think this is where we left, whoops, try again. I think this is where we left off, right?
We left off on the page, like, how we were talking about displacement reactions.
So we were back a bit.
Like chemical reactions, like that whole pyramid thing.
Have we got this?
Well, I think we're on that.
Yeah, we're on
one slide before.
We're on.
So one slide before was double displacement?
Yeah, we just took it to talk.
Okay, so this is just a summary. I'm going to leave it in this mode because in this mode it will let me write on it. When I put it in PowerPoint mode, I don't know why, it freaks out. So we're just going to watch it in this mode. We talked about synthesis, two things coming together making one. It doesn't have to be two elements, it could be two compounds going together making one compound. Decomposition, same thing. One thing breaking down into two or more. Single displacement, a couple, and you either switch out the guy or you switch out the girl. Single displacement. Double displacement, you switch couples, make new couples. Okay, the next type that we're going to talk about is combustion. And we're actually going to go through a lot of these next time. I'm going to shut this other one down. I've got two recording things going at the same time. Sorry about that. Where is it? Okay, shut it down. Okay, so combustion reaction is basically a reaction of a fuel with oxygen producing energy in the form of heat and or light. Most of the time it's a hydrocarbon that we add to oxygen making CO2 and water. Okay, that's a key. If I get CO2 and water, I know it's combustion for sure, but there are other types of combustion reactions that won't give you CO2. They might give you SO2 or they might give you some other oxide. This one is butane. So if you've ever used a butane torch, you need 13 oxygens to go with 2 butanes to make 8 carbon dioxides and 10 waters, and then you get a bunch of energy. Okay, let me go into PowerPoint mode for just a minute. So when we have complete combustion, we end up with CO2, water, and energy. When we have incomplete combustion, and this is what firefighters worry about, is incomplete combustion when everybody starts their furnace, you get carbon monoxide and carbon dioxide. And that's a problem because carbon monoxide is toxic to us. It actually takes the place of oxygen on our hemoglobin and hangs on there. It doesn't let go. It doesn't get deposited. So it makes it hard for our body to breathe. Some of the symptoms that they have, you have with that, are headaches and nausea. People think they've got the flu. And there's this flu goes around all winter, it seems like. So they don't really think about it. And dizzy. Well, that's not really part of the flu, but it could be. I mean, if you're not hydrated enough, you could be dizzy. But then it gets to the point where you can't really catch a breath because of that carbon monoxide hanging on to that hemoglobin. And so there's no oxygen being deposited in your body. It's the carbon monoxide cutting those out. And then you collapse and loss of consciousness and then death if you're not caught soon enough. So if you think you might have carbon monoxide poisoning, the best thing to do is go outside and see if you feel any better. If you feel any better by going outside, you know that you've got carbon monoxide poisoning. You actually need to go into a hyperbaric chamber where they force oxygen into you, forcing the carbon dioxide out by pressure. So some things to know there. Okay, we're going to go into redox reactions now. So this has all been about reactions, this first part. Redox reactions change charge from one side of a compound to another, or one side of a reaction to another. We have oxidation, which is loss of electrons. It becomes more positive. So remember, if you lose electrons, you're losing weight, and you're becoming more positive, like the fat guy up there. If you have reduction, you're actually gaining electrons, and gaining weight can be a negative thing. So you become a negative because electrons are negative, and if you're gaining pounds, it's not a good thing unless you're anorexic. The bottom three are basically just to tell you it's basically vocabulary. So oxidation number and oxidation state basically is what we've been calling charges. Those are what oxidation state and numbers are. Non-redox reactions are when we have a charge on an element. They don't change charge from side to side. So when we have non-redox reactions, it's just regular reactions that we've been working with. Okay? So redox, the elements change charge. Another key for actually identifying redox reactions, if you have an element by itself and then on the other side it becomes part of a compound, or if you have an element that's part of a compound and then becomes an element by itself, that's going to be a redox reaction. That's a clue that you have a change in charge. Looks like the head bobbing's starting to lessen. Okay, we good to go? All right. So when we think about redox reaction, here are two things that will help you remember what is what. Leo the line says GR. So Leo meaning loss of electrons is oxidation, GR, gain of electrons is reduction. Or you can use oil rig. Oxidation is loss, reduction is gain. Whichever mnemonic helps you remember it, use it. Okay? I like Leo the line says GR because it helps me remember GR is negative, and that's that one that's becoming more negative. And I know Leo, I think Leo, there used to be a show with an angel called Leo on it, so I think, oh, that's, so anyway, however you want to remember it. More positive. Okay, so we have some rules for oxidation states. We've been using basic rules to start with, but there are actual rules. The first one is any element by itself is 0 for an oxidation charge or charge. So any element by itself is 0. That includes Braunhifkel and phosphorus 4 and sulfur 8 because they're considered twins or Siamese twins or quadruplets or octets. Okay? Second one, oxidation state of fluorine is always -1. These are some that you need to fill in, so hopefully we're filling them in as we go. Okay? And on the next one, groups 1 and 2 are always a +1 and +2 respectively, with the exception of hydrogen. Hydrogen can become a -1 when it's forced to combine with anybody in type 1. So columns 1 or 2 or the slide, the ones that don't have any other charge but that positive charge. So when hydrogen combines with one of those, it's forced to be a hydride, which is a -1. Okay, another rule. Oxidation state of oxygen is -2, except when it becomes, excuse me, I've got the hiccups, except when it comes to peroxide. And that would be like H2O2, hydrogen peroxide, or Na2O2, which is sodium peroxide. Then it becomes a -1. Okay? Aluminum, boron, and gallium, that's part of our slide, are +3. Algebraically, the sum of a compound always equals 0. So we've been doing these things already. And the algebraic sum of a polyatomic is always just the charge on a polyatomic. Okay, so now I'm going to go out of this so it will let me write. So as we're looking at oxidation states of individual elements, we have to use those rules that we had in order to figure out the ones that don't have rules. So as I'm looking at this one, I would say, okay, sodium had a rule. It was in column 1. There's 3 of them, and they were a +1 charge. So I know sodium's a +1. Plus, phosphorus did not have a rule. So it's going to be our x. So we're going to do some algebra here. Plus, I know oxygen is always a -2 unless it's a peroxide. Well, there's too many elements here for it to be a peroxide. So there's 4 of them, and it's a -2. And there's no overall charge, so it's going to equal 0. So I have to solve for the one that I don't know. So solving down this algebraic equation, I get 3 plus x minus 8 equals 0. So x minus 5 equals 0, and x equals 5. So phosphorus becomes a +5. Okay, so I need to be able to find out what each individual element in a compound or polyatomic charge is for this redox. So let's do this next one here. Dichromate, it has a -2 charge. So chromium, I don't know the charge on chromium. So I'm going to have to put 2, because I have 2 chromiums, x, that I don't know. Plus, I have 7 oxygens. Oxygen is a -2. So I'm going to go 7 times a -2 is going to be equal to the charge of that ion, which is -2. So as I simplify down, 2x minus 14 equals -2. Add 14 to both sides. 2x equals 12. Divide both sides by 2, and x equals 6. So I have a +6 for each chromium. So I'm just doing algebra. Okay, I want you to try, well, let's go to number 4, because I want to do number 4 together, and then I'm going to have you try the others. So on number 4, we actually have to, it's 2 polyatomics. So because it's 2 polyatomics, we sort of need to split it. So we're going to split it into NH4, and I know the charge on NH4 is a +1. That's one of the ones I should know. And I have 2 of those to balance out the SeO3. So what's the charge on SeO3? -2. Now I'm just going to split it down into 2 separate problems. So nitrogen I don't know, plus 4 times hydrogen I know is a +1. So +1 is going to equal 1. Okay, then I go through and solve. X plus 4 equals 1. Subtract 4 from each side, x equals -3. So this becomes a -3. I do the same thing over here with selenium. So selenium I don't know, plus, and I might run out of room, so help we don't. 3 times -2 is going to equal -2. Let me write, thank you. So we're simplifying down. X minus 6 equals -2. Add 6 to both sides, x equals 4. So this is a +4 when oxygen is a -2. Okay, would you take a little bit of time? I'll give you a few minutes. See what you can do with the others. I'm going to give you a 2-minute head start. I'm going to start on the top row and go across and then the bottom row. See what you can do. See if you get the same things I do. And I might just call some of you up. I'm getting tired of talking. Getting it? What you need help with? So you got the x.
Yeah.
Oxygen's always -2, so you're going to go plus 4 times -2.
Okay.
And since it has a charge, it will equal -2.
All right.
Right. If not, then you don't have to. You lose it or you lose it. Okay, let's see. I'm going to pick some faces to put up some numbers here. Let's see, who did I not pick on last time is going to be my first ones.
I feel like that's not entirely true.
Okay, helps to get to the right period. I was looking at fourth, if it's the end of the day too. No, Alex did go last time. Okay, so Brian's not here. Luke, you're up. You're going to do number 2. Emma, you get to do number 3. Cambry, you get to do number 4. Oh, I already did 4. Okay, do number 6. Sorry. Yep, if you got it done. And then let's see. Ben, do number 7. And Richard, do number 8. Tyson, where's your cohorts? Oh, okay. So you're going to have to teach them all, huh? They can watch the videos.
I have a question about finding the charge for this so I can plug it in right now.
So you've got to, that's your X. You don't know it. That's your X. You got to figure it out. Because that can be lots of different ones.
Anything that's in this part
Yep,
of it
anything that's not part of our rules that we just did is going to be X.
Wait, but like the rules that we were talking about right here?
Right there, yep.
Because aren't some of these not a part of the rules? Oh, wait. Like, for example, this one, because I didn't get X in any part of this.
S is in X.
It is an X?
Yep.
Okay, I thought I'd just take the
Nope.
charge.
So we use those basic charges, but now we got to realize they have more than one charge. So if they're not part of those rules, they have more than one charge. If you want to change colors, you can change colors.
I walked in late, so I didn't get the chance to sign in.
Okay, let's get you. Okay, now go. We'll have to wait till they stop writing on the board because it will mess it up. Yep.
If it wasn't for seven, basically, if it wasn't for seventh grade and eighth grade, we would have to use one.
You go on in chemistry, you have to use quad. You have to use the quadratic formula.
I don't want to.
The quadratic formula isn't that bad.
And you have to solve for the one that's the minus b plus or minus the square root of b squared minus 4ac divided by 2a. You have to use that.
I know the quadratic formula. It's mainly like the stuff that we do now, which is like rational functions that we're doing right now, and it's like I understand it.
Let's see, the only one I'm missing is 8. Who's got 8? Okay. What's 8 years of school? Oh, yeah.
They get paid 121 a year though.
That's good pay. I want my starting pay.
You got to go get your farm tech. Get that first.
Buffered in pharmacy.
Right, but get your farm tech first so you can be working in a pharmacy and you get more background that way. And they make pretty good money as farm techs to get through college. Okay, so let me let you log in real quickly. Let's see this one. Okay, log in real fast. Anyone else not logged in? Okay, So as we go through here then, S is a +6, oxygen a -2 here. Manganese +7, oxygen a -2. Iron was a +3, oxygen a -2. You got +4 and -2 here, good. Lead was a +2, oxygen -2, and hydrogen +1. So you need to be able to identify every single one of the elements' charges. Okay, did we have any problems? Thumbs up, I got this. Thumbs down, I don't have any clue. Thumbs sideways, I'm sort of there. Okay, all right, so I know who would need to help. Okay, so we're going to move forward, but I'm going to come back and help those that need it right there. So, oh, I forgot. Yeah, do it from the board. Okay, so as we look at this equation right here, we are able to identify the elements that change charges. You'll notice that they left out hydrogen because hydrogen stayed a +1 on both sides. But the carbon went from a -4 to a +4. And the oxygen went from a 0 to a -2. So 8 electrons were gained by the oxygens because we have 4 oxygens and each oxygen gained 2 electrons. So that's 8 electrons. And 8 electrons were lost by the carbon by going from a -4 to a +4. So as we look at it, redox, we have Leo the lion says, grr. Leo, loss of electrons is oxidation. So the ones that lost electrons, which was a carbon, is the one that's being oxidized. The one that gained electrons, which was our oxygen, is the one that's being reduced. Okay? So we need to be able to identify which one's changing and which one's doing different things. So as we go on to this next one, we're actually going to identify the charges as we go. So first thing you want to do in any equation is write down the ones you know for sure. So oxygen's a -2, any element by itself is 0, hydrogen's a +1, and oxygen's a -2. That leaves me just one that I don't know. I don't really have to do a math equation for this one, right? Because what plus -2 equals 0? A +2, right? Okay, so if we look at it, the reduction part here was copper going from a +2 to a 0. So it reduced by gaining weight. Okay? The hydrogen started at 0 and went to a positive because it lost an electron, therefore it's oxidized. So here we've got an equation like we've been doing that is what type of reaction? What type of reaction is this? You remember? Single displacement. So I got an element, a compound, an element. So that's single displacement. So as we go through there, we could go, oh, zinc is a 0 because it's an element by itself. I know that sulfate, since it hangs together on both sides, I don't need to worry about it changing charge because it's the exact same. And I know sulfate's a -2. Because of that, I know copper's a +2. Because I know sulfate's a -2, I know zinc is a +2. And copper here is 0. Okay, that okay? Those are the equations we're used to seeing. This equation that's shown over here is what's known as a net ionic. And what's happened is you notice that sulfate stayed the same on both sides, right? And because it stayed the same on both sides, they drop it out because they call it a spectator ion. So this would be my net ionic equation. I can see really quickly from my net ionic what's being oxidized, what's becoming more positive. The zinc. So this is my oxidized. What's being reduced? The copper. The arrow went down a little bit too far there, so I'll bring it up. So this is being reduced. Okay, let's go forward to this. And again, I'm going to erase it real quick. All right, now, with this, the only way I can get it straight in my mind is to think of it like a wedding. In a wedding, you have to have a groom and a bride. If you're missing one of those, the wedding doesn't take place, right? So the groom is actually like a bride agent, and the bride is like a groom agent. Okay, so if something's being oxidized, they're also the reducing agent, because redox has to happen together, or it doesn't happen at all. So in order to be oxidized, I'm forcing someone else to be reduced. So if I'm oxidized, I'm the reducing agent. If I'm reduced, I'm the oxidizing agent, because they have to happen together, sort of like a bride and groom have to be together to make marriage. Okay? So this is the equation that we did before. Carbon was a +4, hydrogen was a +1. Oh, try it again. Carbon was a -4, hydrogen was a +1, oxygen is 0, oxygen -2. This would be a +4, +1, -2. What's being oxidized? What's being reduced? What's changing from side to side? What changes charge from side to side? Carbon does, okay. Is it being oxidized or reduced? It is. It's becoming oxidized. It's becoming more Leo. Loss of electrons is oxidation. Okay, because it's being oxidized, it is the Ra, or the reducing agent. Okay, what's being reduced? What's becoming more negative from one side of the equation to the other side? Oxygen. Good. So from one side of the equation to the other, and there's two places where oxygen is, it's being reduced. That means this has become the OA, or the oxidizing agent. Okay? So now thinking that we've got this, we're going to go back and just sort of define each of them. Now, as we look at each of them here, the properties of oxidation agents, that's also the properties of being reduced. And the properties of reducing agent, that's also the properties of being oxidized. So oxidizing agents are reduced, are the ones that are reduced, and reducing agents are the ones that are oxidized. Okay, we still can use Leo, Lions-Hess-Gur, or oil rig to figure out which is which. Okay? Okay, everybody got that down? Basically the same thing we talked about before. Reduced is becoming more negative in oxidation number and gains electrons. That's an oxidizing agent. Oxidized is being more positive in the numbers and losing electrons because it becomes skinnier, and that's a reducing agent. Okay, so the next thing we're going to talk about are batteries. Batteries are redox reactions. If you look at the battery on the left, that is a cheap battery that you can get from the dollar stores. Okay, down the center is a carbon electrode. Around the outside is a zinc. It's just like a zinc foil. So if you've ever cut one of these open, it's like a zinc foil. Between the two, there's a paste, and it has to have a little bit of liquid because that's where your ions move, and it forces your electrons to move around the outside. So you actually get a current because of that. So it separates the two reactions, so you have the oxidizing happening in one place and the reduction happening in another place. And so they have to travel through the wire to get there. Okay, so it's like a switch. If I cut that wire, if I don't connect those two ends, then the electricity doesn't run. Okay, these don't last very long because they're not rechargeable. I can't make the reaction go backwards, and they die pretty fast. Right? Dollar store batteries, you're thinking that. If you go into a Duracell, they've actually got brass that comes down the center where the carbon is, and they've got a little bit more reaction stuff going on, and that's why it lasts a little longer. In the center, we've got a button battery, and the button battery is a mercury battery. And that one of the things they ask you to do is not to especially with the button batteries, please don't put them into the trash, because then they go to the landfills, they degrade, and mercury leaches out of that and gets into our water system. Okay, because the metal little casings for the battery will rust and corrode. So we ask you to recycle those because we can get the mercury out and reuse it. It is a little bit different. Instead of going sideways this time, it's up and down, and you get the electricity going that way. The far battery is a phone battery, and you'll notice it's got some things going on here. The anode is lithium metal. Lithium is very reactive with water, so if you happen to drop your phone in water and it gets in the battery, it's gone. Okay, because it makes lithium hydroxide, and there's no more lithium to be part of your battery, so the battery doesn't work. It does have a nickel mesh that's in there also, so that it can work back and forth, but usually lithium is paired with iodine in batteries so that it can work back and forth and give you the charge that you need. So along with batteries, let's talk a little bit about pacemakers, because this is a chemistry health class. Yes?
Batteries,
Uh-huh.
how does like the battery capacity decrease?
So the battery capacity will decrease because after you've charged it so many times, every time you charge it, it decreases the amount that it can hold the next time. Because when you first do stuff, it's a very perfect line. Okay, think of two strips of metal, perfect. When I start moving it one way, one of the metal electrodes will start to fall apart and go to the other one. Well, when I try and reverse it, when I put it into recharge, it tries to rebuild that strip, but it doesn't rebuild it as a strip perfectly. It now has little bumps and little things going off. So it's not a perfect reconstruction. And you've lost some of the metal along the way. It just won't come back. And so every time you do that, it becomes worse and worse, and finally you end up with a big cluster of gunk on one side, and it doesn't hold a battery charge very long. So that's what's going on. Okay, so with pacemakers, they started with AC units. They would put a pacemaker in, and you had to plug in. That sucked. Okay, so then they started doing battery powered, and you could wear the battery on the outside, and they'd put the electrodes into you. Well, that still sort of sucked. And then they got to the first implantable, one that they could put inside with your heart. And that was pretty big. If you remember, that was down at the U of U. They actually did that down at the U of U. And then we went to a little bit smaller one. What the problem they were finding is as they put stuff into people, they had to be careful what chemicals or what metals they were using because people became allergic to them. And if they had an allergic reaction, they'd actually get like a boil around that pacemaker and then have hives top to bottom. And it could actually cause a reaction in the body where it would start rejecting everything. And so then you have an autoimmune disease. So then they started to do a leadless. So you'll notice this one has leads that would go into the heart and would sort of shock the heart when it got into a wrong rhythm. So now they have ones that they just put in, and they could now just put it into, and it would give enough shock that the heart would restart. Then, now they're looking at something that looks sort of like this little circuit breaker that they put in that doesn't use battery, but uses the chemicals in the body as the battery to charge and to shock them. They've actually now encased them, most of them, in some kind of plastic because the metal starts to degrade and starts to have problems in a moist environment like our body. Okay? Also, other things that we can do with redox reactions, we have redox reactions every day. Every time we eat, we're doing a redox reaction. Every time we breathe, we're doing a redox reaction. We're letting off carbon dioxide and water, and the energy is produced from the stuff we ate we're using to move around. Our homes are powered by redox reactions. Otherwise, we wouldn't be getting electricity to the house. Our cars are powered by redox reactions. The battery, if it's not charged, we can't get this car started, right? And our bodies. So let's look at this next thing here. We're now going to put some things together where we take an equation and we're going to balance it. And then we're going to decide what charge each of the elements have, decide what's the oxidation, what's the reduction, agent and what's oxidized and what's reduced. So first of all, we need to balance this. Sort of ignore this number 1. It shouldn't be right next to it. Okay, so balancing. What do I need to do for this one? Look real quick. What do I need to do to balance it? Okay, aluminum needs what? Okay, I'll put a 2 here. So I'm basically doing this, right? And so we did 1 aluminum, 2 alumins. Now we've got 2. Now we have 2 oxygens, 3 oxygens. Dang, now what do I do? Yes?
Times the oxygen and aluminum.
2 here and 3 here. So then I get 6 and I get 6, but now I have 4. Now I got to come back over here and make that 2 go away and make that a 4, right? So I can balance the equation. So we're doing stuff that we did last time. Now I need to identify the charges. What's the charge on aluminum? Any element by itself, 0. Any element by itself, 0, even if it's a Braun-Hifkel. Okay, we consider 0. Over here, oxygen had a, and aluminum had a, that was one of the that's one of the slide. So it has a specific charge. Okay, so this one I can identify really quickly. What is being oxidized? Aluminum. Woohoo, become more positive. It's oxidized. That means it's my reducing agent. Okay, Alex, you getting this? You writing it down? You need to write it down. Okay, oxygen is becoming more negative, so it is being reduced, and it becomes my oxidizing agent, right? Okay, I want you to take a minute, balance the last 2, sort of ignore that 2 and 3, they were supposed to be over farther. Balance them, determine the charges, determine what's oxidized would reduce, tell me what the RA and the OA are. I am going to have different people come up and do different parts of that. So make sure you're working on it. I'll pass it there. Okay, Aspen, I'm going to have you go balance the first equation, equation number 2. Tyson, I'm going to have you go balance question number 3. One carbon, 1 oxygen, 1 oxygen, 2 hydrogens, 6 hydrogens. So yes, you were right. Sorry.
That scared me.
Okay, sorry. Okay, Jaren, I'm going to have you put all the charges for the number 2 equation above it. Jesus, I'm going to have you put all the charges for the second equation, or the number 3 equation up there above all of them. And then Alex, I'm going to have you identify what's being oxidized, reduced, the reducing agent, and the oxidizing agent for equation number 2. And Kyle, I'm going to have you do the bottom one, tell me the oxidized, reduced, reducing agent, oxidizing agent. Okay? So that little thing like I did up above. So what one's becoming more positive is oxidized and it's the reducing agent. What's becoming more negative is the reducing agent and the oxidizing, reduced and the oxidizing agent. Okay? All right, so as soon as you get your part done, go up and put it up. Nope, hydrogen is a +4. Oh, wait, hydrogen's always a +1, unless it's with column 1, column 2, or the slide. So carbon's not one of those, so it has to be a +1. Hydrogen's always a +1, unless it's with columns 1, 2, or the slide. Okay, as soon as you get the charges, come up and do the charges, or if you know what the oxidizing and reducing agent are, quickly do those.
Right here we had a 0.
Because any element by itself is 0.
So yeah, but like over here.
So that's one of our rules. Aluminum is a +3 always. Oxygen is a -2 always, except in peroxides.
And then when they're separated, which
They're 0.
they're just 0.
Yep.
So this one is going to be
0. Carbon, you have to look at what it's with because it will change. So oxygen's a -2, so carbon's going to be +2. So that was 0. Okay, that one is a +1 always. -2 always. +1 always.
Wait, this one?
No, hydrogen. So because there's 4 of them, that's +4. That means carbon has to be a... No, it's a +1. There's 4 of them. So you're doing... So carbon would be a -4 because it has to add to equal 0. Right? You've got 4 positives. And so carbon needs to be 4 negative in order to add a 0. You need to... That is just balancing. That's when we just put the 3 there. So you're done. So now you just attach what's oxidized, reduced, what's your OA and what's your RA. That was the letter, the unknown letter. Did you do A, B, or C?
Oh, okay.
Do you remember? Did you write it somewhere, I hope? Hey, put down what you think it is. Yep, that's oxidized, and that's reduced. So this will be the RA, and that's the OA. I think they got one of the charges on one of the carbons wrong. I think the first carbon charge is wrong. Should be a +2. So if you want to change that first carbon charge. Use your fist. Just put your fist up there. You got to have not your, yeah. +2.
I had done this too.
Yeah, no, tell me.
Okay, and who did I have doing the charges on the last one?
No.
Is it Jaron? On number 2, okay. Okay, so it must have been number 3. Do you have them for number 3? Okay, let me do them real quick and then we can move on. So here you should have had a -2. When you're done with this, you got -16 and becomes -14. This is a +7. This is a -1. This is a 0. This is a -2. And this is a +6. Okay? Now if you need to, I sort of did the math in my head there, so if you need to write it out, that's okay. Okay, the algebra to it. All right, so we're going to move forward here. Whoops, a little too forward. I want you to try to do these on the left-hand side. So I want you to leave the ones on the right-hand side. Just do the ones on the left-hand side. Identify the charges, identify the redox, or what's being oxidized, what's being reduced, and if you have to, write down the charges. You should be able to look and see which one's becoming positive and negative without actually knowing the charges, right? Because we always write the positive first, and we always write the negative last. So we can really quickly do the redox reaction for it. So I'm going to be calling people up to put that up. Let's see, eeny, meeny, miny, mo. Okay, Aspen, let's you do number 1, Tyson number 2, Cambry number 3, and Emma number 4. So I want you to find what's being oxidized, what's being reduced, what's your oxidizing agent, what's your reducing agent.
I got like 0 and 0.
Right? So what's CS have to be? That's one of our rules. First column. +1. The first one's all, no, that's 0. Any element by itself is 0, but when it comes here, it's +1. And bromine is -1. No, don't do that. That's what you balance it with isn't part of that. 1 minus 1, right? Right, 0, so it had to be 1, right? It has to be a -1 because it's actually this plus x. Well, that's why I'm making you do it. Okay, so which one do you have? 4. Okay, so we have a 0. Any element by itself is 0, so put a 0 above it. Hydrogen, that would be a 0 too. Hydrogen's a +1, right?
Yeah.
Always.
How do you know what they are? Is it from the periodic table?
It's from that list that we just did. So this right here that we filled in, that's not filled in.
I know, I took a picture.
Okay. All right. So then we have chlorine would have to be a -1 because they have to add to equal 0, right?
Oh, okay.
So put a -1 there. Magnesium has a rule. It's in the second column, so it's always +2.
So that would be
And chlorine, in order to balance that out, each of the chlorines would have to be a -1. -1. So the chlorine didn't change from side to side. Because you need 2 -1s to go with a +2 to add a 0, right?
Oh, okay. So,
Yep. So chlorine's not one of our things. Magnesium, hydrogen are. So now connect them and see which one is oxidized, becoming more positive, and which one's reduced, becoming more negative.
okay.
So magnesium is going to what? Just connect the 2 magnesiums. Okay, so you're going from a 0 to a +2. Is it becoming more negative or more positive? So that's going to be oxidized. So you write oxidized, OX, and then because it's oxidized, Mg is the reducing agent, so you put Ra. So then you look at hydrogen. Hydrogen went from a +1 to a 0 because it's becoming more negative. It's reduced. So you say reduced here, and it is the OA. Okay.
I'm just wondering like what the numbers for X are. 'Cause, like,
For which one?
For S.
For silicon, you got to use fluorine. So you got 4 -4, so silicon has to be a +4. Okay, so you had one to do too, right?
Yeah.
Number 1? Okay, so you plus, this is actually 0. Any element by itself is 0.
Oh. But isn't it in the first?
It's in the rules, but that any element by itself is 0. When it combines, it's a +1. So this becomes a +1 here, and that means bromine has to be a -1 to make it add to 0.
Yeah.
Okay, so now cesium, connect cesium with the arrows, or with the lines,
And that's oxidizing?
because it's becoming more positive, right? And it's the Ra. So you put oxidize, and then you put Ra by it.
Oh.
So OX,
And then
Ra, and so this is also the Ra, so you put right under Ra. And then this one right here, because it's becoming more negative, is reduced, and the OA. Okay, go put it up.
So I just got like the numbers, got the zeros right there.
So oxidize, OA, reduced, yep.
Okay.
Okay,
Right or no?
Yes, just you need to make sure you put RA here and OA here.
Okay.
Okay?
And like, it's like you could put truck, like, careful. So, it's bad, all, well, like, if you're just doing the. Really? Yeah, and you can like.
Okay, let's look at each of these really quickly. If you just have elements, this makes it really easy. If you just have elements and they combine, the first one's always going to be positive, the second one's always going to be negative. You don't have to know what number they are. It'll go from 0 to a positive or 0 to negative. So the first one's always going to be oxidized, and we missed the oxidized here, and it is the Ra. And the second one's always going to be reduced, and it is the OA. Okay? So again, the first one's oxidized, it's the Ra. You can't read that. Second one is reduced, and it's the OA. Same thing here. First one, oxidized, the Ra. Second one, reduced, OA. When you have something like this, you have to do a little bit more work on the bottom one. You know that this is a 0, and it's going to go to a positive. So once you figure that out and realize that chlorine is not going anywhere, and hydrogen's going from a positive to a 0, you can really quickly identify that that's what's being reduced, and that's what the OA is and what the Ra is. Are we okay with this? You know how to do it? Okay. So we're going to go forward a little bit more. We're not going to do all of these. We're going to do some of them, just so that we have an idea of how to do them. We're going to do these 8, and then I'm going to leave the others if you want more practice. Excuse me. All right. So we're going to identify what type we have, and if it's redox or non-redox. I need to get a drink. Someone was tickling my throat. Okay. Still there, but try and go. Compound, compound, new compound, new compound. What type? Look at all the different kind. Compound, compound, new compound, new compound. Double displacement. They switch partners. Is it a redox or not a redox? What was the clue for redox? An element by itself. Does this have an element by itself? So it's not a redox. Okay, next one. Compound, compound, new compound, new compound. Double displacement. Redox or non-redox? Okay, next one. Carbon compound plus oxygen yields carbon dioxide and water. Is it single displacement? Is another element kicked out at the end? This one is combustion, guys, combustion. When I end up with CO2 and water or some oxide and water, I'm going to have combustion. Is it redox? It is redox because of this one oxygen by itself. Okay, next one. Lead plus iron 2 sulfate yields lead 2 sulfate plus iron. Is that what? It is single displacement. You'll hear them sometimes called single replacement and single or double replacement. Same thing. Redox or not? Redox because you got two elements by themselves. Next one, compound yielding two new compounds. Is it double displaced? What is it? Decomposition is right. Decomposition, is it a redox? No, it's not a redox. Good job. Okay, next one. Phosphorus plus oxygen leading to diphosphorus trioxide. That's a what? It's a reaction, yeah. What kind? Is it single replacing anybody? No. No, combustion has to yield me water and carbon dioxide or some oxide. Nope, there's no acid or base. Oh, finally, if we go through all of them. Okay, it is decomposition. It's falling apart. Okay, oh, sorry, not decomposition. That's not decomposition. This was. Opposite of decomposition. Synthesis. Synthesis is putting things together, right? If I synthesize something, if synthesize an English lecture, I put it together. Okay, redox or non-redox? Redox. Next one, compound, compound, new compound, new compound. Double displacement. Redox or non-redox? Good. Next one, silver nitrate plus copper yields copper 2 nitrate plus silver. No. Single displacement, because it's an element by itself. It's a what? Redox. Okay, I gave you some others that you can practice on your own, or if you need to come in and get help, that we have something to work with. Okay? Next, we're going to go here. This is where you're actually going to have to start writing the whole equation by yourself. Okay? It gives you it in words, so it's not as hard as it could be, but you still need to do it. So this is another place I like to have scratch paper because I write all over the place. So if you got a piece of scratch paper, put it up by it. So this is my scratch paper. I'm just going to use this next line as my scratch paper and then I'll erase it. So silver 1 means plus 1. Nitrate, if I look on the back of the periodic table, it's NO3 minus. So plus 1 minus 1 already goes together, so I put it together right here. Plus hydrogen, H plus. Sulfide is sulfur, and sulfur is 2 away from being a noble gas, so it's a negative 2. So that's going to be H2, because I need 2 hydrogens to go with the sulfur, S. Gibbs is an arrow. Next one, we're doing silver and sulfide. So I've already got the ions written down here. So silver's a plus 1, sulfur's a minus 2, so I'm going to need 2 silvers, Ag2S. Plus, you guys have not done acids yet, so nitric acid is HNO3. I'll give you that. I got to erase that. Now I got to balance it. So Ag, N, S, H, and O. 1, 2, so I need to put 2 here. Nitrogen, I now have 2 and I have 1. So I'll put a 2 here. Sulfur 1, hydrogen 2, oxygens 6, oxygen, that's a 2 by the way, 6. Okay, so it's balanced. What type is it? Good, double displacement. Redox or non-redox? Okay, remember that double displacement is the only pure non-redox. Okay, let's do the next one, just so we have another one under our belt. So tin is SN, Any element by itself, we just write it, plus copper 2. That means Cu has a +2 charge. Sulfate on the back of my periodic table is SO4 with a 2 minus. So +2 minus 2 already go to 0, so I just smash them. CuSO4 gives is an arrow. Tin 2 plus is, or tin 2 is tin 2 plus. Sulfate was the -2 again, so +2 minus 2, I'm just going to smash them together, always writing my positive first. That's a 4, by the way. Plus copper. Okay, is it balanced? It is balanced. What type is it? Single displacement. Is it a redox? It is a redox. So I've got several others that you can practice with down here, and you can do that. If you have problems doing this, please come in and see me. Remember, if it says like iodine, it's I2. Okay, we've got just a few more to go. So I want to go to this one right here. Now you got to go to the point where now you're only given the reactants. And you got to write the products. Okay, so silver I know always is a +1, right? So that means sulfate is a -2. Sulfate will be a group that hangs together, okay, from side to side for the most part when you have to write your own equation. Copper, for the most part, is +2 when it goes to combine with something. So right now it's a 0, but when it combines with something, it'll be a +2. So in this one, what type of reaction is this? Single displacement. Is it redox or not? It is redox. So I've got two guys fighting over a girl here. So they're going to be flipping out. So copper is going to flip out silver. Now this reaction is actually backwards in real life, so we're going to pretend like it actually works, but it doesn't. So CuSO4 is going to go together because of +2 minus 2. Plus, I'm going to get silver kicked out by itself. Then I've got to erase my charges because they can't be in a final reaction. And I look at it, is it balanced? What do I need to do to get it balanced? 2 by the silver, okay. All right, how many in math have got to the point where you're using FOIL? Raise your hand high. How many have used FOIL before? What does it mean? Right, so first, inside, out, or first, outside, inside, last, right? Well, in chemistry, we take away the F and the L. So all we're left with is OI. Okay, we just do outsides and insides. So when I look at something and I know it's going to be a double displacement, that means they're going to switch partners, right? So I go through and I find the charges. By the way, double displacement is always non-redox. So I have a +1 here with a -1. Calcium's a +2, so chlorine has to be a -1. I put the outsides together. So sodium and chlorine are going to go together. I do not take the subscript. That's a big thing. I do not take the subscript unless it's part of a polyatomic like that. I don't take the subscript. So on this side I have sodium, which is a +1, with chlorine, which is a -1. That's all I need. I don't need to take the 2 over. Okay, then I do the insides, which are calcium and iodide. So calcium is a +2. Iodine is a -1, so how many do I need? So I2. Then I erase all my little drawings right here, and I say, is it balanced? Is it balanced? What do I need to do to balance it? I need 2Cl where? Okay, in front of Na, so there's 2Cl. Good. All right, so last one here, what type of reaction number 3? This is the last one we're going to do together. Synthesis, right? The only thing I do is put those two together. I can't double displace them, I can't single displace them, I can't do any of that, right? So, Alex, is it redox or non-redox? %50 chance.
When
It is redox. Anytime you start with an element, it's going to, or have an element, it's going to be redox. Okay, so oxygen likes to take what charge? Right now it's zeros, but what charge when I put it together with something? -2. What's hydrogen going to be? Always +1. I always write my positive first, so it's going to be hydrogen first, oxygen second. And how many hydrogens do I need to balance it? 2. So I'm actually making water here. Is it, whoa. Is it balanced? Okay, what do I need to do to balance it? 2 oxygen, where? What side? On the right, in front of the water. Okay, and 2 of the hydrogen gases. Okay, so you should be able to do something like this. Now, I left you a lot that you can practice. If you need help, practice it, come in, so I can help you out. I don't want to go through every single one because I found that if I do all of them for you, then you're not learning. Okay, so if this is hard for you, this is where you need to come in and get help. I'm almost done for today, so hang with me. Okay, we are going to also be doing, what we've been doing right now is molecular equations. That's equations like we normally write them. Okay, the ionic equations is where we split out anything that's aqueous into its ions, because that's what happens when it is put in water. It actually splits out into its ions. Okay, the spectator ions are the ones that are the same on both sides, so we can count them out. So that was like that sulfate in that equation that you saw that I said, oh, that's a spectator ion, we're going to drop it out, and we get the net ionic equation, which is just what really is happening. The others are just there. Okay, now this is not in your notes, so flip to the very back page because this is going to be on the test and you're going to need it. So your black page is blank, it says review, but go ahead and put this down so that you can get this next little part that we're going to be doing. We got 3 more slides to do, maybe 4 if we have time. Okay, to get us all at the same place. So molecular equation, just a normal equation like we've been doing. Ionic equation, that's where I split the ones that are AQ into their ions. Spectator ions are the ones that are the same on both sides of the reaction, exactly the same. Okay, and the net ionic equation is cutting out those spectator ions, so they're no longer spectators. Okay, right after this, after you get this written down, just so that you know, this is sort of just vocabulary, and we'll be actually doing those in just a minute. But we're going to watch a little video. I'm going to turn off the lights. Please don't fall asleep. It's not very long, but you do need to write down what this video says. I know her voice is a little annoying. It's okay. Mine is too. So you'll get over it. Okay, we got a basic idea of what each of these are. So molecular is normal equation. Ionic is where I split the ones that are AQ. So only the ones that are AQ. The ones that are gas, solid, liquid, I don't split. Okay, just the ones that are AQ. And spectator ions are the ions that are the same on both sides of the reaction. So if you have something in math that's the same on both sides of the reaction, you can cancel them out, right? That's the spectator ions. Net ionic equation is what I'm left with. Okay? All right, we will be going through each of these again, so you can, if you didn't get the notes down for that, you can do it. I want to go on to the thing here. Go ahead and thank you, the lights. Okay.
Hi everyone, in this video, I'm going to teach you how to learn your solubility rules really easily.
So write this down on the back, you're going to need them.
So the way I remember solubility rules is to think of someone sagging his or her pants. Please never sag your pants. Nobody appreciates it, and we'd much rather not see you like that. But anyways, this mnemonic does come in handy, and this image does come in handy when you need to learn solubility in chemistry. So the way to remember all the molecules or substances that are always soluble, you think of NAG-SAG. Always soluble elements. NAG-SAG, I mean molecules. So the way to remember...
Sorry, let me just start that. So, whoa, try it again. I was trying to be helpful and it's not working.
Your solubility rules really easily, and my name's Shilpa. So the way I remember solubility rules is to think...
It's not letting me. Ah. Honestly, it's really getting me irritated.
Hi everyone, and this is it, and we must solubility in chemistry for substances that are elements, NAG/SAG, I mean molecules. So the way to remember NAG/SAG is to remember that whenever you sag your pants, somebody's going to nag you. So the N in NAG/SAG stands for nitrates, NO3 minus, the A for acetates, C2H3O2 minus, and G for group 1, the group 1 metals such as lithium and sodium, and many more. S is for sulfates, which is SO4 minus 2. A is for ammonium, NH4 plus. And lastly, of all the soluble ones, group 17 nonmetals, such as fluorine, chlorine, bromine, iodine, and more. Even though I told you that these elements and molecules are always soluble, I lied, because there are two specific groups that are exceptions. Now, the very first group I like to call PMS, and it's very easy to remember, just 3 letters. And the P stands for Pb plus 2, which is lead. The M stands for mercury, diatomic mercury, Hg2 plus 2. The S for silver, Ag plus. And the second exception, or before I go on to the second exception, I'm just going to make things easier for you and put a nice magenta asterisk next to PMS, and then put a magenta asterisk next to the sulfates and group 17 nonmetals, because PMS is never soluble with the sulfates or the group 17 nonmetals. Now let's move on to the second and final exception. This exception is called Castroware. Castroware. And Castroware, the reason it's given that name is because it's calcium, strontium, and barium, all from the alkaline earth metal group. And Castroware is never soluble with sulfates. So you see that beautiful neon green asterisk next to Castroware? Well, we're also going to put one next to the sulfates because it's never soluble with the sulfates. And I suppose since now we know 2 exceptions to NAG/SAG, NAG/SAG's not always soluble, but it's almost always soluble. Good luck with.
Okay, I'm going to leave that up for a minute so you can get it down. This is something that you'll need to know, and we'll be using it in a lab coming up. So hopefully that will help you. I know, we're almost done. We're just going to practice it, and it'll be done. I know, I told you this chapter is very full of lots of stuff, and it is. Okay, did everybody get that down? Anybody need it again? Okay, we're going to actually practice it. Let's go ahead and turn the lights back on. Okay, so here, you'll want to have an example down, so keep this on the back page if you got room on the back page. If not, get you out a piece of paper so you can practice. This is the molecular equation, okay? So it's NaCl2 and goes to NaCl, 2NaCl plus I2. You'll notice that they're all AQ. If it's an element, you don't want to split it. So a total ionic, I would split this one into 2 Na plus AQ plus 2 I minus AQ. This one I would just bring down, plus Cl2 AQ. I put the arrow in. NaCl is going to split into 2 ions. Okay, it's going to be Na, we're going to have 2 Na plus AQ plus 2 Cl minus AQ. And then we get one more at the very end, which is the I2 AQ. Okay, so what can you tell me? Which ones are the same? Which ones are the same on both sides? Cl2 is the same on both sides? It has to be exactly the same. Na is, good. So Na and Na, is there any others? No. So Na becomes my spectator ion. It's the one that's going to cancel out on both sides. Okay? To make the net ionic equation now, we just write everything that's not Na. So anything that I haven't circled, and I write it down. 2I minus AQ plus Cl2 AQ gives me 2Cl minus AQ plus I2 AQ. Okay? Got it? Okay, I got one more for you, and then I'm just going to cut it. I want you to try practicing it on your own. Okay? Can you? I'm going to enlarge this and start it from here so you can see it. Hopefully that's a little better. So practice and see if you can do that on your own real quick. We just got a few minutes, but you should be able to